All right, so Matt, let's talk about what these variables in the equations mean. First off, what is this v with a line over it?
V is average velocity.
Perfect. Average velocity. What does delta x mean?
Delta x is a change in position.
Perfect. And what does delta t mean?
Delta t is the change in time.
It's important to note that delta means the change in. Nice. What is this a with a line over it?
That would be average acceleration.
Nice. Delta v,
Delta v would be the change in velocity.
right? And delta t again?
And delta t would be the change in time.
All right. For practice really fast, I want you to read through it like this. Average velocity is equal to the change in position over the change in time.
The average velocity is determined by the change in position divided by the change in time.
Perfect. Can you do it for the second equation?
Average acceleration is determined by the change in velocity divided by the change in time.
Awesome. Let's do this for the next three equations. What does VF mean?
Does that mean final velocity?
Perfect. That means final velocity. What does V naught mean?
So that I don't know.
That means initial velocity. So some people write that as VI. I like to write it as VO or V naught.
Okay.
Okay. What does A mean?
Is that average time?
It's not average time. The A itself is just acceleration.
Oh, it's acceleration times time.
Exactly.
Okay.
So can you read this equation as if it's a sentence?
Yes. Final velocity is determined by the initial velocity plus acceleration times time.
Awesome. Good stuff. Let's move on to this next one. What is XF?
That's final position.
Perfect. What is X naught?
That is initial position.
Right? What is V naught?
That is initial velocity.
Perfect. What is T?
That would be time.
Right. And A
A is acceleration.
and T. Time. Can you read this like a sentence?
Final position is determined by the initial position plus the initial velocity times time plus 1/2 of acceleration times time squared.
Awesome. Good stuff. We're going to do this for the third one. Matt, what does VF mean?
That is final velocity. No, wait. What is final velocity?
It is
Sorry.
final velocity. All good. What does V naught mean?
That is initial velocity.
Perfect. What does A mean?
Acceleration.
Nice. What does XF mean?
That would be the final position,
Yes. And X naught?
the initial position.
Perfect. Can you read this entire equation like a sentence?
Yes. Final velocity equals initial velocity squared.
Careful, let's
Oh, do I
start
have to-
again. We forgot the squared initially, right?
So this is how we find final velocity squared.
Exactly. We're solving for final velocity squared here.
So I'll start again. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the final position minus the initial position.
Perfect. Another way to think of this entire part is delta x, or the change in position, right? Sometimes the equations are written that way with delta x instead of x final minus x initial. Now we're going to be using these equations to actually solve problems. We just covered the entire chapter review as far as equations go. Now we're going to do a few practice problems. So we're starting off with speed and velocity. If you're driving 95 kilometers per hour along a straight road and you look to the side for 2 seconds, how far do you travel during this inattentive period?
We're trying to determine the distance traveled. So we know how much this 2-second stint, how much that takes up in the whole journey. But you need to know what the whole journey is to be able to make that calculation.
Right. And we're going to simplify this as much as we can. What variable is represented by the 95 kilometers per hour?
That would be... Oh, it's the velocity.
Velocity. Is it the
Yes.
initial velocity, final velocity, or average velocity?
This would be the average velocity.
Perfect. What is the 2 seconds represented by?
The 2 seconds represents... Would that be time?
Yes.
Okay.
So what equation do you have that uses average velocity and the change in time?
Okay.
Oh, one more thing. What are we solving for?
We're solving for velocity, but the change in velocity.
That's not quite right. What does it say? It says, how far do you travel during this inattentive period? So it doesn't say how fast are you traveling. How fast might be a speed or a velocity. It's asking how far. How do you measure distance?
Would this be position?
We're solving for delta x, or the change in position. What equations do we have on hand to solve that?
Final position equals the initial position plus the initial velocity times time plus 2 times time squared.
We're actually going to be stuck in these more basic equations up here for now.
Okay.
But actually, wait, say that one more time. Say exactly what you just said.
I thought it was final position equals the initial position plus the initial velocity times time plus 1/2 of the acceleration times time squared.
Let's try it, actually. I don't think that's incorrect. So, we have final position equals initial position plus v naught t plus 1/2 at squared. So I'm going to rewrite this really fast as x final minus x initial equals v naught t plus 1/2 at squared. Can you tell me what I just did there?
The problem was adapted so we can actually subtract 2 of the variables we know.
I just subtracted x naught from both sides, right?
Yeah.
Perfect. And this x final minus x initial is delta x, isn't it?
Yeah, that's the average?
The change in position.
Okay.
Remember, if it was average position, it would be x with a dash over it. Delta in front of it makes it the change in. Okay, let's go ahead and start solving this. We're solving for delta x. Do we know the initial velocity?
The initial velocity is that 75 miles an hour.
Yeah, 95. Perfect.
Okay.
We're going to go ahead and do it like that. We have delta x equals 95 kilometers per hour times, what is our time?
Our time is 2 seconds.
Time is 2 seconds. Plus 1/2. Do we have any acceleration?
Are we talking about the acceleration from the moment you started the car from nothing and then hit 95? Or are we talking about you are driving 95 from the beginning?
Exactly. You're just driving 95.
If that's the case, then I don't think there's acceleration. I think it's just a consistent speed throughout.
Right. We can assume a constant velocity here. So we're going to say acceleration is 0. And then it doesn't even matter that the 2 seconds here is squared because all of this, anything multiplied by 0 is 0.
And the 1/2 times 0 will just become 0 as well. And then we can just focus on the beginning of the problem.
Exactly. Now, we have an issue here. We're trying to multiply kilometers per hour times seconds. That's going to give our answer as kilometer times seconds over hours. And that's confusing. That's not really a clear distance, is it?
No.
So, we need to convert this 95 kilometers per hour. I want us to convert it to meters per second. So first, how many meters are in a kilometer? Kilo, for example, means times 1,000. So if I run a kilometer, I'm running 1,000 meters. If something weighs 5 kilograms, then it weighs 5,000 grams. Kilo means times 1,000. All right, let's get back to this. So kilo is 1,000. We have 1,000 meters per kilometer. This will allow us to cancel out kilometers on top, kilometers on bottom there. Then we need to get rid of hours. How many hours per 60 minutes?
1.
1. we have 1 hour per 60 minutes. And I'm just going to finish this off, 1 minute per 60 seconds. So I'm going to cancel out hours on bottom, hours on top, minutes on bottom, minutes on top. This literally becomes 95 times 1000 divided by 60 squared, or 60 times 60 on bottom. And we're left with the units meters per second. This is a tough concept. We're going to do more unit conversions later. But for now, we're just doing it for this problem.
Okay, so 60 squared, I think, is 3,600. And that's the first thing we do because we have to do the exponent.
Yeah.
Now we have to do multiplication next. Could we simplify the fraction before we multiply by 95?
You could, or you could just do 95 times 1000 divided by 3600.
So I'm good to do the division problem first before I multiply by 95. Okay.
Yeah, with PEMDAS, multiplication and division, it doesn't actually matter the order, neither with addition and subtraction. This is a good time to use a calculator. In physics, we don't want to be doing all this math long form, because then these questions are going to take forever.
The good news is I have 3, but the decimal I'm a little hung up on, so I will use a calculator.
So yeah, I get 0.39 meters per second. Is that what you have?
Oh, I have 3.6. Wait. Oh, because I didn't multiply by 95. Okay. Okay, I didn't do that part.
No worries. Unit conversion.
Oh, I got what you got.
Perfect. Nice.
All right, I got it.
So, now we took that little side route to do our unit conversion. We're back to our main problem, and we can plug in our answer. 26.39 meters per second times 2 seconds is equal to the change in position.
It's 26.39 times 2.
Perfect. And you'll notice that the seconds should cancel out. So it's just going to leave us with meters at the end, right?
Am I right that we're at 52.78 meters as our answer?
Perfect. 58.72 you said?
Oh, I said 52.
That's right. My bad.
Oh, good. Oh, good.
All right, and what's the unit?
The unit is meters per second.
That would be velocity.
Oh. Is it just meters then?
Meters. We're just calculating a distance.
Okay.
And notice the seconds here and here canceled out.
So that's why it just left us with meters.
Exactly. Let's look into that a little closer really fast. We had meters per seconds times seconds. This is almost as if the seconds are in the numerator. Meters times seconds over seconds, and seconds will cancel out because they're in the numerator and the denominator, right?
Right.
This happens a lot. In physics, it's unit analysis, and you have to make sure that your units at the end match up with whatever type of answer you're getting. So this time we were calculating a distance or a change in position, and we were left with meters, which is a unit of distance. Really fast, I like how you actually used one of the 3 basic kinematic equations. Another option would have been to use one of these basic equations. Average velocity equals the change in position over the change in time. Here's a trick. You never actually really have to use these. If you have these, you can always solve the problem. A lot of physics teachers will give 10 or 20 equations based off the situation. If you know how to read the situation and plug it in using our 3 basic kinematic equations, let me be very specific about which are the 3 basic kinematic equations, then you can solve any problem in kinematics.